Welcome. We are very excited to present EL3XIR, our work on fuzzing commercial off-the-shelf secure monitors to you. Just to give you a brief overview of this talk. So we looked at ARM Cortex-A targets, and as many of you probably know, you typically have these 4 exception levels, and we concentrated on this highest privileged level down here, the exception level 3, which is typically called the secure monitor. And as it has so much privilege over the system, with this privilege comes a lot of responsibility, and developers working on this need to be very, very careful about not to plant exploitable bugs in there. So this is why we came up with some fuzzing infrastructure, which is the combination of fuzzing and rehosting to take proprietary secure monitors, plug it into an emulator, and find the memory corruption bugs that are potentially still in these targets. So who are we? I'm Marcel. This is Christian. We're both having an academic background at the FAU in Erlangen-Nuremberg. That's in Germany. I'm currently a postdoc with the HexHive at EPFL. That's in Switzerland. And we're both specializing in systems and software security, rehosting, a lot of fuzzing, and all sorts of stuff. So to zoom out a little bit, this secure monitor, so that you have an overview of what kind of devices we're talking about, you probably know that these ARM chips are used in smartphones and tablets. Maybe you know that it's used in your smart TV, but you might know that there are many, many other device categories where these chips are used. For example, this smart hub here that you can see on the slide, infotainment systems in your cars, the Starlink user terminal, and your favorite drones by JDI, and many other categories of devices. So, and what vendors typically do, they take this reference implementation by ARM themselves, which is called the ARM trusted firmware, fork it and modify it. And as you can see here on the slide, the majority of the language used in this target is C, which leaves the room open for all sorts of memory corruption bugs and logic bugs, as the low-level developer is used to. So here now in the audience, why should you care about this? Okay, and I brought you 2 motivating examples. One is the more product-oriented motivation, where you're part of a blue team, a red team, or a third-party auditor of code, and you want to go through some sort of certification, the common criteria. And this slide here shows that Samsung, for some of their devices, this is the example, the Samsung Galaxy S22 and related devices, they went through this, and the ARM trusted firmware down here in red was part of this assessment. The other motivation is more when you're motivated by money. So Pontoon here in the background, they have infotainment systems and all sorts of devices that are powered by ARM devices. And of course, typical bug bounty programs like the one by Google here, where, as you can see, the trusted execution environment is an interesting and worthy target to be investigated. So with that, we have introduced you to the secure monitor, and I think we motivated that it's a very juicy target. So what does it actually do? So the secure monitor has a bunch of very hardware-related features, right? So the replay protected memory block is typically implemented there. It's taking care of power management, the world switching from the normal world to the secure world. Typically, you will find some crypto hardware. It's involved in secure boot and many more features. So as you can see from these features, this is all very system on chip and hardware specific, right? And that leads to a lot of fragmentation in this ecosystem, meaning that the code is typically not looked at by many, many developers since it's not a common ground, and this fragmentation typically leads to less audited code. And in addition to that, these extensions of the ARM trusted firmware are typically closed source. So even if third-party people wanted to look at that, they don't easily have the chance to audit the source code. So on ARM v8 application processors, you typically find these privilege levels that I've introduced before, but also this world separation here into the normal world and the secure world. And starting at the least privileged level, where you find the typical user space apps, we go one level below, where you typically find on the left side the embedded Linux that you are all familiar with probably, or on Android devices like the Android derivative of Linux, hypervisors, and then down here, this fragmented mess of the ARM trusted firmware, which is modified and derived from the ARM trusted firmware by a range of vendors. So, and while looking at this, I think when you just intuitively think about the secure monitor, you would think of it as this gateway of just making the communication between the secure world and the normal world possible, and managing the shared memory infrastructure between these two worlds. And the secure world side here has been covered by a lot of previous work. And the target of this specific work here was to target the secure monitor itself and kind of go deeper into all of these hardware-related features that I've introduced before. So this attack surface here, the secure monitor call from a compromised normal world down to the secure monitor, is the focus of this work. So yeah. There has been a lot of related work on all of these topics. We're kind of standing on the shoulders of giants. Without all of these people here and many, many more that we probably forgot, our research would have not been possible. But if you kind of skim over these, only a few have been focusing on the secure monitor, and even less have been focusing on like automated techniques to enable like dynamic execution or fuzzing for these devices. So we ventured out and we're asking ourselves, okay, where's the advanced fuzzing infrastructure for these devices? So in last year, we presented Tease here at hardwear.io, and maybe you remember this talk and the struggles that we went through to actually fuzz stuff on devices. So if you have an actual device, you need to take care of it rebooting. You need to somehow interface reset buttons and make it somehow work, and you just cannot scale. So fuzzing on hardware is really, really hard. This is why we're taking a very different approach for this target that we're looking at here right now. So, and since we made these bad experiences in the past, we came up with a little wish list of what would you like to have when you're fuzzing like very low-level components on ARM chips. And one of them is typically introspection, right? So if there's a bug triggered, you want to detect this bug. You want to have some sort of introspection capability to actually see, okay, this is some sort of buffer overflow. For techniques like coverage-guided fuzzing, you need to somehow introspect the target to understand if you covered more of the control flow graph. And in triaging bugs, actually having dynamic like execution capabilities is just absolutely necessary. Then for fuzzing, target reset and like having reproducible like inputs that lead to crashes and determinism is absolutely essential. And then of course, the more executions per seconds we have, the better it is, since we can find more bugs, right? So horizontal scalability is like one of these properties that you really, really want when you're fuzzing a target large scale. And with this wish list, we're going to go into the like details of EL3XIR, and Christian is going to walk you through these.
Perfect. Thanks. And let's dive into the technical details of our talk. And we just saw all of these capabilities we want when analyzing secure monitors. And one technique that promises to solve all these is emulation in the end. And the intuition is rather straightforward. When we can emulate or run the secure monitor inside an emulator, we can easily introspect it, and we can actually then scale the process basically arbitrarily. And so our plan was pretty simple. Yeah, we started out, and the first thing you need is you need an emulator. And the basic idea is that, well, we just use QEMU, right? QEMU has already support for ARM devices. It has support for the ARM trust zone. And then the next step would be take a fuzzer. Okay, just take AFL. AFL can be easily plugged into QEMU. And then the idea is that we can scale this process and run it on commodity hardware, like for example in the cloud, and then we can find a lot of bugs. Nice plan, but we soon realized, well, it's not that easy. It's not super easy because these proprietary secured monitors, they don't run out of the box inside QEMU, obviously. So this was kind of a problem. So, but if we go one step back, we realize, well, we want to run this in an emulated environment in the end, because as we saw, on-device analysis is no real option here. So other idea, what about full emulation? Yeah, we could just extend QEMU, extend it with all of that stuff that we can run basically an entire Android software stack inside our emulator. Good idea, but we are only 2 people. We don't have time to build the next full-fledged Android emulator. So other idea, what about rehosting? Yeah, rehosting, the basic idea is that we don't build a full emulator, but we just build simple or smaller peripheral models that mimic some of the hardware at least. And then maybe we can run Android in all of the software stack. Well, if you just take a look at an ordinary smartphone and all of those sensors that are based on the smartphone, you soon realize that even with that approach, you will have to implement a huge number of peripherals in QEMU. So that's also not really feasible. So instead, what we can also do is a fourth option. We do partial rehosting. And the basic idea here is we focus on exactly that software component that we want to fuzz. And in that point, we are looking at a secure monitor. And the idea is that we can then save the effort to run Android or all of that other stuff in our emulator. Okay, how can we do this? And for that, take a look back and look at the smartphone. Forget Android for a moment. Also forget the Trust Zone, the Trusted OS, and all the trusted apps. We only want to run the secure monitor binary. And this could look something like this. Yeah, we are building or running our secure monitor inside an emulator, and we are building around a rehosting environment that keeps the secure monitor basically alive inside that emulator. And first of all, what we then need, obviously, is we need to handle these hardware interactions. And then we can focus on exactly only hardware that directly interacts with the secure monitor. So, for example, if you think about a screen driver or something like this, we don't need that stuff, yeah? Android is not important for us at that moment. But it's actually not that simple also, because even if we support that hardware, we still, at some point, the secure monitor will interact with these other components. Yeah, it will talk about via the SMC interface or with the bootloader. So we have to somehow, at least to some extent, support these other software components. And our idea here was that we basically replace them with simple, smaller software stubs that mimic to the secure monitor their behavior, essentially. And the idea is that we can then trade basically hardware dependencies for software dependencies in the end. So what we have then is two construction sites. We have to handle these software dependencies to some extent. And I will introduce them a little bit more in the next slide. And we have to handle a smaller set of hardware interactions. Okay, so let's start with these software dependencies. And maybe to show you better what I mean by that is following along the typical ARM boot chain, which you can find on Android devices. And a little bit simplified here, yeah, all vendors can do or change up their boot chain a little bit. But in the end, what's happening is we have a bootloader stage 1 and 2 here, maybe from a boot ROM, and they will just set up some initial hardware and bootstrap basically the secure monitor. So the secure monitor is the third bootloader stage that's running basically. And what it's doing is it starts up, it sets up some paging and other initial stuff. And at some point, it want to switch to the Trusted OS. It will boot the Trusted OS. And for that, what it's gonna do is it will execute an exception return instruction, yeah, that will switch the CPU from EL3 to EL1 inside the secure build. And then the next step is that the Trusted OS will have its time to boot up. And then the Trusted OS will boot. It will boot also some trusted apps or other components. And when it's finished, it will give back control to the CPU or to the secure monitor via executing a secure monitor call. And inside the secure monitor call, it will also signal to the secure monitor, I booted up successfully, basically. And then it's the secure monitor back. The next step inside the boot chain is it will do some housekeeping maybe, and it will prepare the CPU for the first initial switch to the normal world. And then at that point, it's happening a similar thing with the secure world. It will issue an exception return instruction, which will switch to the normal world. And then in the normal world, you will find all of those other bootloader stages for setting up Android and all of that other stuff. Okay, but now remember, we don't want to run all of those components. We only want to run the secure monitor. And then we want to replace up these other components with basically simple software stubs. And how can this look like? I brought you an example here of a bootloader which we implemented. And our approach is basically we just write a smaller set of assembly instructions. And then we want to mimic to the secure monitor all necessary parameters and functionality such that the secure monitor can actually boot. And this basically boils down to our bootloader writing some stuff into memory, some parameters. And for example, it will set a pointer to a struct which holds information on how to boot the rich OS and the trusted OS in the process. And after we set all of those must-have parameters, what we want to do is we set up the CPU to prepare to jump to the binary, to the secure monitor binary that is already placed inside the memory. Then we will configure the CPU, and in the end, we can just execute a return instruction and jump to the secure monitor. We can place all of that bootloader inside memory, and we can start our emulation basically here at the first instruction. And then this would look something like this, yeah. As you see, we replace the entire bootloader, BL1 and BL2, with our super simple assembly instructions. And this will allow us at least to start the secure monitor. The secure monitor will boot up, start booting up. Okay, next in line, remember what's happening. The secure monitor will at some point try to boot the trusted OS. And how can we handle this now? Well, we actually follow a pretty similar approach. What we're doing is we are replacing the complete trusted OS here with a simple software stub, yeah, that only executes this SMC instruction that signals to the secure monitor that the trusted OS booted successfully. And actually this is enough to let it know that, well, yeah, it all went good, the trusted OS is up. Yeah, just keep going. And that's what a secure monitor will do, yeah. It will go on, will do some internal housekeeping, and at the end, remember, it will switch to the normal world. And now what's happening here is our attack model now here kicks in, because we wanna basically inject inputs via this interface to the secure monitor. So we can replace the entire rich OS and this entire Android, this huge software stack, with a simple SMC instruction that can allow us to basically send arbitrary SMCs later on during fuzzing to the secure monitor. And we will see how we can do this later on, a little bit more in depth. For now, what we want to do is we just take a snapshot of the booted up system, yeah, that we can later use during fuzzing for super fast resets. Okay, perfect. Software dependencies basically solved. Again, we have another dependencies to solve. Those hardware interactions. Yeah, the secure monitor will obviously interact with hardware, especially also during boot, and it mostly does this via MMIO. And at its core, MMIO is super simple. Yeah, you're writing at a specific memory region to send data to a peripheral, and you are reading from a region to receive data back. And what we saw when we analyzed some secure monitors is that they basically mostly do configuration of hardware during boot up. So they are writing some configuration value, and then they are polling on an MMIO region to check for the peripheral for its answer. And usually what they're doing, they're just answering with flipping a status bit or something to let a secure monitor or the firmware know, yeah, the configuration went good. Just keep going. And well, we have a problem here now, because in our emulator, we don't have any peripherals. So there's no one answering, obviously. So what else, what we now have to do is we kind of have to handle this, else we will just end up in an endless loop, yeah, and our firmware will get stuck. And our idea is here, shown here on the slide, and it's actually pretty simple. What we are doing is we are setting breakpoints at those MMIO polling locations. And then what we can do is we are writing the expected values, the status bit, for example, exactly into registers, into these CPU registers that are read from these MIO ranges. Yeah, and this will basically signal to the firmware that that there is a peripheral. Yeah, and the intuition is rather straightforward. Yeah, we are not really hardware here. We are just pretending to be hardware, and the firmware will allow or believe us if we are just returning the correct value in the end. And here at the end, when the secure monitor boots, at some point you saw it will switch to the normal world, and what we're gonna do is we also set a breakpoint there, and then we can simply take a snapshot at the location. Okay, perfect. Everything's set up. So let's plug in a fuzzer here. So which ingredients do we need? First of all, a rehosting environment. We just saw how we implemented this. Then a snapshot of a booted secure monitor. We just created that one. Perfect. And so the third component, a fuzzer. And now when we think about fuzzing, a basic idea is that we need to analyze the attack surface of our target. And then we can think about how we can inject input into this attack surface. And for that, we looked at secure monitors, and basically what they do is they expose this SMC interface to the rich operating system. Yeah, and there's our attacker local. So the rich OS can send basically arbitrary SMCs to the secure monitor. And what's happening inside the secure monitor is that based on a specific register value in EL3XIR, it will derive a function identifier. Yeah, and based on that function identifier, it will forward a request to a specific service. And what vendors now do is they usually implement those so-called runtime services themselves. And here on the slide, you can see a function signature of such a runtime services, and you see they are not really strongly typed or something. They are pretty loosely defined, this interface. So there are several tens of unique APIs, yeah, and that's not super good for fuzzing, yeah, because a fuzzer will have a hard time guessing meaningful values in here. So, but in fuzzing, we have actually a solution for that, and that's called, we are writing a harness, yeah. We are writing basically a harness that knows how to inject this input. And yeah, you can do that. You can write a harness, but after maybe 10 harnesses you wrote, at some point you're realizing, well, it costs a lot of time. This is super cumbersome. There got to be a better way than writing those manually. And what we then did, we took a step back, and we realized, why should we write those harnesses ourselves? Why don't we, because we know someone who knows how to effectively inject inputs. And that's basically these Linux drivers. These Linux drivers that issue these SMCs, they know how to put input into this SMC interface. So our idea was, why don't we get inspired by these Linux drivers a little bit? And that's exactly what we did. So we built basically a pipeline that allows us to automatically generate harnesses that are tailored specifically for a specific secure monitor. And our pipeline basically boils down into 3 steps. First of all, we are taking the Linux or Android source code, and then we are compiling a partition of it using LLVM. And what this allows us to do is that we can do basically data flow analysis on this partition. And then we localize SMC call sites inside that partition, where SMCs are executed. And then we follow for each of those parameters that are sent, we follow them back to find out their type and other things. And this allows us to basically prototype a function function signature that looks like that matches hopefully those of a real runtime service. And what we also did is, in the third step, we take all these candidates that can be function signatures, and we probe them against our snapshot ones. Yeah, and the basic intuition here is that for all runtime services that are for all function signatures that lead to the same runtime service, they will have a unique coverage profile in the end. Yeah, and all of the other ones which are not backed by a runtime services, they will leave into the default case. Yeah. So this last step allows us to prune basically false positives away, and we also can find new runtime services that maybe were not used by a rich OS. Okay, so with this pipeline, in the end, we have a fuzzing harness that is super tailored for our target. So let's start our fuzzer then. And what we see here is basically our fuzzer is super slow. Yeah. We have a minimal number of executions per second, and the problem here is that we have a lot of hangs and timeouts. And maybe you already guessed it. Where do they come from? It's MMRO again. Yeah. And this time it's a little bit worse. Yeah. Because in the first step, we could easily, guess or through reverse engineering get the return value that the firmware expected, because those were mostly just flipping a bit or signaling okay. And this time it's worse because the firmware now really interacts with the peripheral. Yeah, it will send data, and then the peripheral will maybe dynamically calculate a value that will be returned. And we cannot expect that we can manually implement these peripherals, and that these are really working, and that the firmware really believes us. So that's a problem. And our idea was, we could just automate this process to some extent. And that's our basic idea here, shown on the slide. We called our approach reflected peripheral modeling. And the idea here is that we basically save the effort of manually writing these peripheral models. Instead, we let a fuzzer take on this task. And if you look down here, you see this fuzzing input. That's just a stream of bytes, basically. And what we are going to do is we take the first initial bytes to fill our SMC request. Yeah, that's our attacking input. Yeah, that we send this to our harness that will inject this into our target. And then we treat the remaining bytes after that a fuzzer gives us as input to the MMIO interface, actually. And what we are doing is we have implemented a mechanism that allows us to stop the execution or hook the execution at exactly locations where this secure monitor does MMI read events. And this can look as follows. Yeah? If you look at a physical memory layout of a secure monitor, what we see here is we have those bootloader stubs, secure monitor stubs, trusted OS stubs and our binary in here, and we have basically a huge chunk of MIO here, also in our layout. And under the hood, we are using avatar 2, and what we can do there is we can use functions like add memory range that will basically just add or define that our emulator has a physical memory backed at that location. What we can also do is we can write in these memory regions, and we use that for example, writing these stubs, software stubs into memory. And there's also a third option, and this is a function called add in-memory buffer peripheral. And what this allows us to do is that it will basically stop the execution at that location and then request us for specific input. And what we are now going to do is we are basically forwarding this request because we don't know what we want to return. We have no idea which peripheral is behind that region, and we are forwarding this request to our fuzzer. And our fuzzer will eventually, it's obviously not hardware, our fuzzer also doesn't have no clue which peripheral is backing up this memory region, but after enough executions, our fuzzer will eventually come up with a good value. And this allows us to basically, emulate peripherals in an automated manner. And here in the end, now you can see an overview of our fuzzer, which we called EL3XIR. We saw our three main components in the talk. First of all, we are running a snapshot of the booted secure monitor, and we can create a snapshot using our rehosting framework, which I just presented. Then at number 2 here, you see we are using a refined fuzzing harness that knows how to effectively inject these inputs into the secure monitor, and we have an automated pipeline for creating these. And at number 3, you see that we are using our technique, which allows us to create MMIO interactions on the fly that will keep the secure monitor running. And since we are coming from academia, we had to evaluate our research, and that's basically what we did. We choose a number of targets, 7 targets here, and with EL3XIR we triggered 17 security relevant bugs in 5 of those targets, and after responsible disclosure we got until now 6 CVEs assigned. Okay, and with that we want to see EL3XIR in action, and for the demo I give the word back to Marcel.
Thank you, Christian. Okay. So now we've seen all of these nitty-gritty internals of EL3XIR, and now we're going to go into a demo that we have prepared to you. And I'm going to give you a little bit of context about the bug that we're about to rediscover. And this goes back to 2019, where Zhong Jing here at Infiltrate 2019 was giving a talk about some of the Huawei devices that were very popular back in the days. And he found a bug in this exception level 3, the secure monitor, that allowed him to get arbitrary code execution inside of the EL3, and with that, the compromise of the entire secure world, right? So the concrete device we're looking at here is the P20 Lite. Was kind of a popular device back then. It was released in 2018. Like the one that we're looking at was running Android 8, and this is a high silicon Kirin system on chip. And the idea is now that we went through obtaining the binary for this secure monitor, and we did all the reverse engineering to actually boot it up to the normal world so that we have the actual attack surface, right? And then we plug in the fuzzer at this point in time, and we start injecting inputs so that you can see how EL3XIR works in action. What Christian is doing here, he's booting up EL3XIR for the first time. This is the entire boot process up until the rich OS is executing for the first time. There, we take a snapshot. And the second stage, we kind of launch AFL using this snapshot every time to, from a fresh state, execute SMCs with randomly generated inputs into the secure monitor. So what you see here is the typical AFL++ status screen. It's a bit of an outdated version. You can see we have for a fully emulated target, that's ARM running emulated on x86, a reasonable amount of executions. We're discovering edges, and the demagogues are with us today. The Fuzzer already found the bug, presumably, that we're looking for. At the bottom here, these scrolling messages that you see is the MMIO accesses, right? So we have the address that the secure monitor is accessing during execution, and on the right you see the randomly generated value that we're taking from the fuzzing input to kind of try to roll the dice for the value that lets the execution proceed, so that we can discover more of the control flow graphs and the target. So that's EL3XIR in action. If you want to check it out, this is all on our GitHub repository. I think we can go back to the presentation. So the bug that we found here, I want to drill a little bit deeper into this. So this little assembly snippet that you can see here, when you use our framework, you can attach a debugger to this and you will end up in this basic block. And the line highlighted in red here is the data aboard that you will see. So X20 plus some hex, you will read from some unmapped memory. Just to make our lives a little bit easier, some pseudo C code where there's this magic region in memory that we are reading a value from. Turns out this is the where the global data of the trusted firmware lives. We're saving this in X19, adding some more offsets, doing some sanity checks. Then we're dereferencing with an offset from that again, and using this value as a function pointer, essentially. Right? So this is a function table here. A function pointer table. So, and luckily there is another SMC call where this is happening. And this is essentially allowing us, since we control X0, to write a value to this exact address where the pointer to the function pointer table is located. Meaning that we can kind of set the base address of the function pointer table using the first gadget, and then using the shared memory infrastructure between the rich OS and the secure monitor can basically point it to a region of memory that we control. And thus, we, in the end, can craft a fake function pointer table that will allow us to get code execution in here. And from there, it's easy game. You figure out your rob gadgets, get read primitives and write primitives, and then go for it, get arbitrary code execution down there in exception level 3 on these devices. If you want to play with this, the exploit will be made available in this repository. And Moritz Blei, who did his bachelor thesis with me, this was work he primarily did, so thank you, Moritz, at this point. And if you're interested in more low-level details, this is kind of the rediscovery of a bug that was already discussed in 2019. You can check out the original recording of this. With this, we're reaching the end of our talk on EL3XIR, fuzzing commercial off-the-shelf secure monitors. I hope you enjoyed it. Feel free to check out our Git repository. We went through academic artifact evaluation, so all of that stuff should be there. If not, reach out to us and ask us any questions that you want, and then we're happy to take your questions. Thank you very much.
Thank you, Marcel. Thank you, Christian. Do we have questions in the audience? Yes.
Hi, thanks for the talk. So about the newer CVs, are those under some embargo or something, and what type of bugs you could think to find in EL3 implementations, or was there any bug pattern that you found? Was it straight up buffer overflows or these type of function pointer setting things, or anything you can shed light on? Thanks.
I'll take the first part, you the second. So the CVEs that you saw on the slides, the CVs are assigned, and we went through responsible disclosure to get them. And the second question was about the severity of the bugs, right? Type. The typical memory corruptions that you find. Yeah. And do you want to talk about the severity?
You can read and write out of bounds and at that point. And since the secure monitor is part of the trust zone, you can also compromise your trusted app or trust OS and then steal basically personal data. Yeah.
Thank you. Do we have any other questions in the audience?
Hi, great talk. Thanks. I was here. I was pretty surprised that when doing the MMO fuzzing thing, that it's enough to just give it some random values and then it's happy pretty quickly. Whether did you find more difficult hardware to emulate or something like that?
A very good question. It's the idea is that that it's not super easy to find those values. That's why we let a fuzzer find them for us. And the fuzzer will try multiple values. And at the good thing is that the firmware will internally basically return a get value via MIO, and then it will have checks down there that check that the value is sane to some point. And since the fuzzer optimizes for coverage, it will at least find a value that falls out of those error cases. So at some point it will find a good one that goes through. And that's exactly the good one for us. Yeah.
We have a question on the other side.
So thank you for the talks. I have two small questions. One, does EL3XIR support multi-threading? Like, can you do multiple SMC calls at the time to try to find a race condition? And the second one is, did you try to make custom mutators to improve the fuzzing results?
I'm not sure that I got the first one correctly, but about a second one, we could manually implement mutators, and we did so to some extent. For example, the SMC, the function identifier, we know at least something about how it should look like. But that's basically what our harness synthesis already does. It will generate a good harness that includes those mutators to some extent at least. And we also implemented some smaller custom mutators that specifically can fuzz the SMC interface better. Yeah, we did it.
Okay. And the first question was, does the fuzzer handle concurrent SMC handlers? Like, or there is only one, like in your pipeline at the harness, wait for each SMC calls to finish one at a time.
Oh, yeah. So we did not look into like concurrency related bugs. Okay. I'm actually not sure if untrusted firmware kind of locks the critical paths inside, but that's a very interesting like next project. We're looking forward to your pull requests.
Nice, thanks.
And maybe if I can add something on that, we also only sent one SMC request. We did not build up any state or something like this, but this could also be a super interesting extension. Yeah.
Thanks. Do we have any last question? No? Yes.
Just out of curiosity, did fuzzing the return values from the hardware cause any bugs?
Yeah. So you're basically talking about like a thread model where the MMIO accesses and the values returned from there, creating bugs. We did not encounter any of those, no, but that's also an interesting one. Yeah. Yeah.
All right. So you've got food for thought for next couple presentation, I guess, right? Let's give another round of applause to Marcel and Christian.